Today we will be looking at and understanding the Kariba Dam in Zambia and try to understand its plunge pool problem it's experiencing. Additionally, we intend to suggest potential solutions within the scope of our EME 303 course.
The Kariba Dam, designed by French engineer André Coin, is located in the mid-Zambezi Basin, connecting the Zambezi River to Lake Kariba. Construction began in 1951 and concluded in 1959. The Kariba Dam provides a cheap source of power for both Zambia and Zimbabwe. The reservoir supplies water to two underground hydropower stations, with a total capacity of 1,800 megawatts, generating more than 10,000 gigawatts of electricity annually. The current issues that are leading to the deterioration of the dam is the plunge pool. A plunge pool occurs in the area where the water hits the ground. The plunge pool has grown to be 10 times bigger and deeper than the originally expected dimensions. The basalt the dam lays on is eroded away, causing the infrastructure supporting the dam weight to become unstable, which if the dam falls would take out 40% of the hydroelectric capacity in all South Africa and destroying lives and everything around it.
To understand the root of the issue, we conducted a two-dimensional free jet calculation modeled after the dam to simplify and understand the forces at play. Using the height of the gate relative to the top of the dam of 20 meters, we used Bernoulli's equation to calculate the exit velocity of the water to be 19.8 meters per second. From the exit velocity, we use the kinematic equations to calculate the impact velocity where the water enters the plunge pool. To translate this velocity into pressure, we once again use Bernoulli's equation, obtain the pressure of approximately 801 kilopascals. To convert this pressure into force, we assumed from the image that the free jet made contact with the water as a circle with diameter of 10 meters. With these results, we calculated the force exerted to be 63 megatons. However, it is notable to mention that there are many assumptions made in our calculations, such as the lack of air resistance, that would overestimate this value, but the real force would still retain a considerable amount of this estimate. To visualize this force, the newest SpaceX Starship currently produces a maximum thrust force of about 76 megatons during launch, so it's safe to say that the forces acting from the falling water are extreme and show why hydroelectric is a reliable source for power. This high force environment, combined with the presence of high weathering basalt at the base of the plunge pool, is the perfect combination for the issues we see today.
How could we fix this within the scope of the course? Well, using the model that we formed in the last simplified example, if we decreased the initial velocity, this would decrease the pressure on impact. This decrease in pressure could be formed in multiple ways. The way we suggest is by putting some sort of steel beams across the exit point. This would firstly decrease the velocity of the water by increasing friction. This decreased velocity would, in turn, decrease the force on impact. Additionally, having these bars go across the outside would heavily increase the turbulence of the water. And if we consider the air resistance we neglected in the previous example, this would massively increase the air resistance of the water. Therefore, the velocity upon the impact and the force it exerts is going to be significantly lower. In conclusion, the solution to put steel beams across the open points of the gates, though simple, would be an effective method in reducing the impact pressure and therefore the erosion under the plunge pool. Though this conclusion may not be the most effective method to use when considering factors outside the scope of this course, we believe that this solution demonstrates a particular understanding within EME 303. Thank you very much.